Everyone, I'm Irfan. Welcome to my channel. The paper I've selected for today to go through with you guys is Add Math Paper 2 from May-June session 2022. So without any further ado, let's go ahead and start with question number 1. In question number 1, I'm given an equation of a curve and I'm told that the domain is all the x's greater than or equal to 0. I have to find the exact value of y when x is equal to 6. I'm also given specific requirement which I have to show my answer as a cert. So first thing first, of course, we're gonna substitute all the x's with 6, and this is the fraction I'm gonna get. However, I need to rationalize this. What I'm going to do here is to multiply top and bottom by the conjugate of the denominator, which is 3 minus the square root of 6. Once you do that, in the denominator, you can use the famous identity difference of squares, which is basically a squared minus b squared is equal to a plus b times a minus b. So going backward, I already have the right hand side and I can obtain the left hand side by simply raise 3 to the power of 2 and square root of 6 to the power of 2, which results in having 6. In question number 2, I'm given the graph of two functions. However, the first one, f of x, is the absolute value of that, and for g of x is just a straight line, and I'm supposed to find all the x's from f of x which is less than g of x. In other words, I have to solve this inequality, and graphically basically what I'm supposed to do is to find all the x's that is trapped between x1 and x2, and that's where the absolute value of f of x is less than g of x. It's below g of x. Now, before I try to find x1 and x2, you have to understand that g of x is a straight line. So I have to find the equation of that. Also, I have to do the same thing for f of x. For g of x, it's not a difficult task. You're all familiar with the famous line y equals to x, which is passing through origin at 45 degree. So if you just shift this guy 1 unit down, it's gonna cut the y-axis at -1. It's also gonna cut the x-axis at 1. So basically it would be x minus 1. So that's a shortcut. However, if you cannot recognize this immediately, you can always attempt to plug in values and find the equation of the line from the famous formula y equals to mx plus c. C is already known, that's -1. M is also rise over run. Rise is 1, run is 1 as well. 1 divided by 1 is 1, and you eventually gonna get the same thing. For f of x, however, the story is a little bit different because there are two scenarios I could think of f of x. F of x could be a straight line like that, which after I implement the absolute value, I have to flip the part which falls below the x-axis and just bring it up, and this is what I get. Or I could think of a line like this, which has a negative slope, and then when you mirror it about x-axis, this part which is below x-axis, it comes up, and eventually you're gonna get the famous V shape. That's why I came up with two answers. However, it's not gonna affect the final answer. Both of them is correct. However, if you choose either one of them, you need to stick to it till the end of your work. So over here, I selected 2x minus 5. Now, how am I gonna find the slope as well as the y-intercept? Well, basically the y-intercept is -5 before you flip it and you get +5 up here. And also finding the slope, it's easy because all I have to do is to find rise over run, and rise is 5 while run is 2.5. You can also do that by plug in numbers because you have 2 points, 2.5 and 0. negative 5 and 0. Or you, as I said earlier, you can think of f of x to be a line with negative slope. You should get the same thing in the end. Now, how am I going to find x2? Well, be aware that x2 is the intercept between g of x and the positive side of the f of x. Therefore, I'm just going to leave f of x as it is, 2x minus 5, and I equate it to x minus 1 or g of x, and that gives me x minus 4. For finding x1, however, you need to consider the negative part of the f of x. That's why you see this negative in front of the function f of x, and you have to implement that before you start solving it. Again, it's going to cut g of x. That's why on the right hand side I have the equation of g of x. Well, you expand the negative, therefore you get negative 2x plus 5 equals to x minus 1. X goes to the other side, become negative 3x. 5 goes to the other side, become negative 6. The negatives from both sides basically cancel out. You divide both sides by 3 and you're gonna get x to be 2. I knew from the beginning that my answer is all the x's between those two, and that is what you see here. Question number 3. I have to find the possible values of k for which this quadratic equation has real roots. So the key word is here, real roots. If you're dealing with real roots, whether it's distinct or repeated roots, the discriminant or delta or b squared minus 4ac should be greater than or equal to 0. The reason I'm including the equality as well is because we're not told that the real roots should be distinct. As long as they're real root, the discriminant should be greater than or equal to 0. So my b over here is k plus 5. You make that substitution. A is k and c is negative 4. You make all the substitution. You expand these brackets. For over here, you get 16k. This guy, you just have to expand it. You can use the famous identity square of sum, which is the first term square plus double of their product plus the second term square. Therefore, I get k squared, 5 times k, double it, 10k, 5 squared is 25. I can add up the like terms. I get k squared plus 26k plus 25 is greater than or equal to 0. I can factorize this simply by saying what are the two numbers, their product is 25 and their summation is 26. So those are obviously 1 and 25, and this has to be greater than 0. Now, the last part, if you want to solve this inequality, you need to find the critical values. So the critical values are obviously the roots of these linear factors, and those are negative 1 and negative 25. And my parabola looks something like that. And it's going to cut the x-axis at these 2 points that I just mentioned. Why am I drawing this? Because it gives you a better visualization of what's happening. I want wherever my quadratic or my parabola is above x-axis, is greater than 0. And that is this part and this portion right here. So that means all the x's less than negative 5 and all the x's greater than negative 1, and that's why you see these two inequalities here. Question number 4. Variables x and y are related by this equation, and x has to be greater than 0. It's quite obvious, otherwise it would make these two fractions to be undefined. I have to use differentiation to find the approximate change in x when y increases from 4 by small amount of 0.01. So obviously this is the formula that you guys have to use when you have to deal with small increments and also differentiation. First thing first, I have to take derivative of my equation. You can do that over here by rewriting the equation of the curve and bringing all the x's up, but you have to change the power negative. This makes it easier for you to take derivative. The derivative of constant is 0, obviously. The derivative of 2x to the power of negative 1 -1 goes in front. You have to subtract 1 from the existing power, which becomes -2, but then it goes down and become positive. Same thing here, -2 goes in front. That's why I have this -2 here. And then you subtract 1 from it, you get -3. Again, bring it down, you get +3. And then I have to find this value when the x is 1. Now, when the x1 is come from, if you read the question, they say change in x when y increases from 4 by this small increment. So when y is 4, what is my x? That's the question that you need to answer that. Otherwise, you cannot make the substitution and find dy by dx. That's why at the beginning, it's a good idea just to make a substitution of y to be 4 and attempt to find the value of x. Once you do that, you multiply both sides by x squared to get rid of the fractions. This is obviously a quadratic equation. You bring all the terms to one side, you get 3x squared minus 2x minus 1 equals to 0. You can simply solve this by factorizing. So since this is a prime number, obviously this has to be 3x. This should be x. The reason I put -1 and +1 here is because when I multiply 3x by -1, I get -3, which when I add positive x to it, I get -2x. You can basically use any method for this factorization, whatever method that you have mastered already. So that leads to x to be 1 and -1/3. However, I have to reject the idea of x to be negative because my domain says x has to be positive. So when y is 4, x is 1. That helps me to actually find the value of dy by dx. So I just replace all the x's with +1. That leads to -2 minus -2, which is -4. Now this formula that I showed you at the beginning, the left hand side is complete, that's -4. The right hand side, I'm given the small increment for y, which is 0.01, but I have to find the small increment for x. And I can do that by simple cross multiplication and then divide 0.01 by -4, which results in -1/400. Question number 5. I have to solve this equation. Now, if you look at this equation, this is an exponential equation because x is in the power and all the bases are basically multiples of 5. So I'm gonna use my knowledge of the law of indices and factorization to simplify this fraction, and hopefully we can get to the final answer. So 625 can be written as 5 to the power of 4. Same goes to 125 can be written as 5 to the power of 3. And then I'm gonna cross multiply, so basically bring this guy up. At the same time, I'm gonna multiply 3 to x to the power of 3. Do the same thing here, 4 times this guy, because if I have a number and it's already raised to a certain power, if you want to raise it again to another power, so the law says you have to multiply those two numbers, and that's what I did here. So it simplifies to this. However, don't forget here you should add the powers because you're multiplying two numbers with the same base but basically different powers. So it should be +1 and not -1. And once you get to this point where the bases on both sides of the equation are the same, you can put the powers equal to each other, and obviously that's a cubic equation. You gather all the cubic terms on one side, the constant on the other side, you end up with x cubed to be -3. And lastly, how do you get rid of this power 3? You can take cube root of both sides, which results in x to be cube root of -1. Part B. In part B, I have to sketch the graph of this exponential equation and also indicate any interceptions. Well, you can use the fact that all these exponential equations, they either look like something like that or they decay rapidly, and they all have an asymptote which starts from x-axis. So these three also tells me that I need to shift my principal axis or my asymptote 3 units up. However, for finding the y-intercept, you have to be careful. The y-intercept is not 4 anymore, because the normal exponential curve, it passes y-axis at 1. So students might think that if you shift everything 3 units up, now the y-intercept is 4. However, don't forget that my curve is being stretched along the y-axis because I have a coefficient in front of e to the power of x. So the best thing is just to put x equals to 0 in order to find the y-intercept. When you do that, e to the power of 0 becomes 1. 4 times 1, 4 plus 3 is 7, and that's it. Question number 6. Question number 6 is about bearings. So we have a cyclist who rides at a speed of 4 meters per second on a bearing of 15 degree. Write the velocity vector of the cyclist in the form xi plus yj. And we are also told that I and j are unit vectors due east and north respectively. So if you recall about bearings, we have to always start from north and then go clockwise, and according to the angle that we're given, we just rotate clockwise and then we stop. So this is 15 degrees. So this is the line of the action of the cyclist. So all I have to do is now to break this vector, which has a magnitude of 4, into I and j form. So here's what you can do. There are two basically possible ways to look at this. Either consider this angle, which is 15, or consider this angle, which is 75. So what I did, I just used this angle, which is 15. Now if I want to find j, so basically it's 4 cosine 15, that give me j, the coefficient of j, and 4 times sine 15 gives me the coefficient of I. In part B, I'm told a vector of magnitude 6 on a bearing of 300 degree is added to a vector of magnitude 2 on a bearing of 230 degree to give a vector v. I have to find the magnitude and bearing of v. So it's always a good idea to have a visualization of what's really happening. In this scenario, we have a bearing of 300 degree as I have drawn here, and also a 230 degree. So basically these are the two vectors that I'm dealing with. So I have to break each one of them into the I and j component, and then add the I components together and j components together as well. So for the first vector, the value is 6. However, if you notice, I put negative 6 here because when you break it into its I component, it is due to west and not east. Therefore, you should have a negative there. And then I used sine 60. Well, you could also use cosine 30 if you want. I just used the remaining angle to complete one revolution and get 360 degree. And also for j, I used again same angle, and that is cosine of 60 degree, and it's in the positive direction because it's going north. For the second vector, same thing, it's I component, or the projection of it on the x-axis is negative. So I used how much it needs further to complete 3 quadrants. So we've already gone through 230 degree, another 40 degree to the x-axis, and therefore I'm going to use cosine 40 for the I component, and for the j component we're going south, so therefore it has to be negative, and it is sine 40. As soon as you get the vectors in this format, the rest is easy, because the addition of vectors, you can simply add them up, the I components together, j components together. However, you need to find the magnitude of it, which you can use Pythagoras theorem. you just raise each of these components to the power of 2, add them up together, take the square root, and that is 6.94. Now, for finding the angle, when you want to use this formula, the arctan of y over x, which is basically the coefficient of j over coefficient of x, you need to know where you are. So if you look at the vector v, I already know that I'm in the fourth quadrant because I is negative and j is positive. So I want to find this angle. So you can just take j to be 1.714 while the I is 6.728. So once you use the calculator, you get the value of 14.3, and make sure it's in degree and not radian. However, this is not the final answer. You are supposed to find the bearing, and bearing always starts from north direction and go clockwise. So I have already completed 3 quadrant, that is 270 degree plus this 14.3 degree. So the final bearing is 284.3. Question number 7. I'm given an equation which looks like a fraction, and I have to differentiate it with respect to x. Now, this might look a little bit complicated at first glance. However, if you still recall how to take differentiation of a fraction, you just have to use quotient rule. That means take the denominator, raise it to the power of 2, and then in the numerator, first you take derivative of your numerator multiplied by denominator untouched, and subtract by taking derivative of denominator multiplied by numerator. Now over here, this might be the tricky part where student might struggle, because when you want to take the derivative of numerator, which is this guy, you have to use product rule as well as chain rule. So the product rule, in the sense that this is e to the power of 4x, that's one function, and this is another function, tan x. So if you take derivative of e to the power of 4x, you get e to the power of 4x. You just basically copy paste it and then multiply it by the derivative of the power, which is 4, and that's the chain rule I was talking about. And then multiply it by the second function, and then add it to the derivative of second function, which is secant square x, times the first function, which is e to the power of 4x, and that's the derivative. You can leave it like that. You do not need to tidy up. After all, the question only carries 4 marks. Question number 8. I have function f, which is defined as 3 sine square x minus 2 cosine x, where the domain is between 2 and 4, and x is, of course, is in radians. In part A, I have to find the x coordinate of the stationary point on the curve of y equals to f of x. And I want to refresh your memory that the stationary point is a point where first derivative is equal to 0. Therefore, I have to start by taking derivative of this function. Now, if you notice, the first function is 3 sine square x, which is a composite function. Therefore, I have to apply chain rule. That means I'm going to take derivative of outside. So the power 2 goes in front. 3 sine square remains there, except you have to subtract 1 from the existing power. And then don't forget to multiply by the derivative of inside, which is the derivative of sine x, and that is cosine x. And then the second function, 2 cosine x, you just simply take derivative of cosine x and ignore the coefficient. And as you all know, the derivative of cosine x is negative sine x. So after you tidy up, you have to put it equal to 0, since we're aiming to find the stationary point. Then it is very obvious that 2 sine x can be factored out. I'm going to be left with 2 sine x times 3 cosine x plus 1 equals to 0. Therefore, it's either the first term is equal to 0 or the second term. So if 2 sine x equals to 0, therefore sine x has to be 0, and that leads to x to be pi. And that is within the domain because pi is 3.14. and that falls within my domain. That's acceptable. However, when you put the second expression equal to 0, you get cosine x to be negative 1 over 3. And if you use your calculator, the first value you get is this. But then if you refer to the unit circle, if this is negative 1 over 3, so inverse cosine of negative 1 over 3, that would be this guy. And also there is one more angle, which its cosine is negative 1 over 3, and that would be 4.37, falls in the third quadrant. And both of them are rejected because my domain is defined between 2 and 4. Therefore, this is the only answer that I can find for question number 8. Question number 8, part B. I have to solve the equation f of x equals to 1 minus 3 cosine x. So from the previous part, I know the definition of f of x. All I have to do is just substitute it with its equivalent value and then bring everything to one side. I'm going to be left with 3 sine squared x plus cosine x minus 1. Just like solving any other trigonometric equation, I must have same or united function. Therefore, I either have to get rid of the sine and convert it somehow to cosine, or do the same thing for cosine. So I would rather change the sine square x to 1 minus cosine square x, because therefore the argument will remain to be x, and it's also one of the easiest trigonometric identity to apply here. And then you just expand this bracket, you get 3 minus 3 cosine squares plus cosine x minus 1 equal to 0. If you rewrite everything in descending power of cosine x, you get this quadratic equation, which I rather to multiply everything by -1. Therefore, my leading term is positive. And now all I have to do is to solve this. You can use factorization or any other method. You can also call this, if it's very difficult for you to start factorization, you can introduce a dummy variable. For example, call this y or a, and then continue from there. But don't forget to convert it back to the word of x once you solved for y. So however, I did not use that approach here. After you factorize it, put the first factor equal to 0. Therefore, you get cosine x to be -2 over 3. Also for the second one, I get cosine x to be 1, and the result is 0 and 2 pi. However, this should be rejected because, again, don't forget my domain was between 2 and 4. But for the upper one, it is acceptable. Again, if you refer to the unit circle, there are two answers. When you take the inverse cosine of -2 over 3, this is one of the answers that I get. And then if you pass pi, you get to the second angle. And both of them are acceptable since they fall within the domain. Question number 9. In this question, I have this diagram, which is a circle, and from a point T outside this circle, two tangents are drawn to this circle, and it's gonna touch my circle at point P and Q respectively. I am also given the subtended angle here, which is 2 phi. I'm asked to show that tan phi is 2 phi in the case when the area of the sector OPQ is equal to the area of the shaded region. I'm gonna just go ahead and use this piece of information that I'm given. So what is the area of the sector OPQ? That is half of the subtended angle times radius square. And don't forget the radius here is a, so therefore half of 2 phi a square I have on the left hand side. This should be equal, according to the question itself, should be equal to the area of the shaded region. And for the shaded region, my approach is to find the area of this right angle triangle, multiply it by 2, I get the other, because this is symmetrical, and then subtract the area of the sector OPQ. Therefore, I'm going to be left with the shaded region. That's why here you see, first of all, I did the half of base times height. Well, the height would be A, the radius. The base is PT. However, because I don't have the value of PT, but I can replace it somehow with other values which connects to radius and phi. So if you look at this angle, this is half of 2 phi, which is phi. And according to the tangent, tan phi should be opposite over adjacent. So that would be PT over A. And if I make PT the subject of the equation, I would get A tan phi, and that is the base of my triangle. And in the end, I multiply it by 2 because I want the whole area. I want 2 of the triangles together. And then lastly, I need to subtract by the area of the sector, which is the same thing as I got on the left hand side. Now, don't forget to replace PT with A tan phi. If you do that, I get A square tan phi, and basically I got A square everywhere. You can cancel that A square as well, but before that you can bring this to the left hand side and you got 2 phi a theta because these two terms are identical. And then once you cancel out the A square, you left with tan phi equals to 2 phi, and that's what I'm asked to show. Therefore, it is shown. In part B, I'm told that in the case when the perimeter of the sector OPQ is equal to half of the perimeter of the shaded region, find an expression for tan phi in terms of phi. Now, again, I'm going to use the information given to me in the question and start with and see where it leads. So the perimeter of the sector OPQ is basically OP, which is the radius A, plus OQ, which is also the radius A, plus the length of this arc PQ, which is the subtended angle times radius. So that would be 2 phi A, as you can see here. And on the right hand side, I need half of the perimeter of the shaded region. Now the shaded region, I have PT plus TQ, which are basically the same because outside any circle, you can draw 2 tangents to the circle which have the same length, and also plus the arc length PQ. So that is basically shared between these two regions, and that is again 2 phi A. However, don't forget to multiply it by half because the question specifically says half of the perimeter of the shaded region. And I have to get rid of all the weird letters and make sure everything is in the word of either A or phi. And I've already proved in part A that PT equals to A tan phi. Same thing goes to QT. So I'm going to replace them with their equivalent value. And after that, I'm going to tidy up. A tan phi plus A tan phi is basically 2 A tan phi. And I can cancel the 2 from here and here with the half which is outside, and I'm gonna be left with A tan phi plus phi A. And you can bring the phi A to the other side and group it with its like term which is here, so that's gonna reduce to phi A. And lastly, if you cancel the A from all sides, you have tan phi which is equal to 2 plus phi, and that's the final answer. Question number 10, part A. A geometric progression has first term A and common ratio R where R is greater than 0. The second term of this progression is 8. The sum of the third and fourth terms is 160. In part I have to show that R satisfies this equation. So I'm going to start with what's given to me and basically change some notations from the conventional one. So instead of U1, we have A, that's the first term. u2, since it's geometric, so it's basically 8 times common ratio, and that is 8. So right there I can find a to be 8 over r. Why? Because I'm gonna use it in the next part. So u3 and u4 are ar square and ar cube respectively, and if I add them up I get 160, and that's what I'm told in the question. So replace the third and fourth term with its equivalent values in terms of a and r as I did here. Factor out a, but then I want everything to be in terms of r. After all, the equation I'm supposed to find, everything is in the word of r. So a is replaced with 8 over r, and then you expand it. That results in, oh, before you expand it, I can cancel 8 from both sides. So 160 divided by 8 is 20. And over here I got r plus r square, and bring everything to the left hand side, and you're gonna get what we have up here. And in part 2 I have to find the value of a. So since a is 8 over r, that means I need to know the value of r. Therefore I can substitute it. So that means the equation you found up here, you just have to solve it. And I prefer factorization because it's quite an easy quadratic equation to be solved using factorization. All I need is to find out the two numbers where their product is negative 20 and their summation is 1. And those numbers are negative 4 and positive 5. Therefore, the first factor leads to r to be 4, which is acceptable here. However, the second answer is not acceptable since r has to be greater than 0, and that's what I've been told here in the question. Therefore, if r is 4, a divided by 4 is 2, and that is the value of a. In part B, I'm no longer dealing with geometric progression. Here we have an arithmetic progression which has the first term p and common difference 2. The qth term of this progression is 14. A different arithmetic progression has first term p and common difference 4. The sum of the first q terms of this progression is 168. Find the values of p and q. So if I have an arithmetic progression, therefore I can apply the general rule which says the nth term is a plus n minus 1 times t. However, since here I do not have the nth term, the general term is mentioned by q, so therefore the qth term is a plus q minus 1 times d, but d is known, that is 2 right here, the common difference. So I just replace it. Also, instead of the a or the first term, I use the letter p, and that's what I get. Also, I'm told the qth term of this progression is 14. Therefore, when you expand this bracket, you get 2q minus 2. That should, the whole thing should be equal to 14. You tidy up, and that gives you an equation in terms of p and q, which I have to solve. Therefore, I need another piece of information which I can get from the second statement. So let's see where that leads us. Over there, we're talking about the sum of the first q terms. So I'm gonna apply the general formula. So if you're talking about the sum of the first q terms, therefore I can say q over 2 times 2p, which is the first term, plus q minus 1 times 4, which is the common difference. And when you expand it, you get pq plus 2q squared minus 2q. Don't forget the 4 also should be expanded here before you get rid of the square bracket. And this whole thing should be equal to 168 as mentioned in the question. And you get, it seems I'm dealing with a quadratic equation. However, if you combine equation 1 and 2, you can get rid of one of the variables. In this case, I'm getting rid of the p. So I'm gonna replace all the p's. Actually, there is only one p right here. I can replace it with 16 minus 2q, as you can see here. Then you expand this bracket, you get 2q squared minus 2q plus 16q minus 2q squared, which is 168. So 2q squared with 2 squared is gone, and positive 16q with negative 2q is 14q, which is equal to 168. Therefore q is 12. As soon as you find the q, you can go back to equation 1 and substitute q with 12. Therefore it leads to p, which is negative 8. Question number 11. In question number 11, I'm given a cosine curve graph, as you can see here, and you are supposed to find this shaded region up here. Well, there are a few ways actually you can solve this question. This question carries 9 marks, and first glance when you read through it seems very difficult, but it's really not, if as soon as you establish your plan and how you want to approach this question, what strategy you want to use, the answer kind of reveal itself to you. So there are a few ways you can use. However, the method that I'm using here is basically, first of all, I'm gonna find the area of the region A, and then I'm gonna subtract it from the whole region here. The integration of f of x minus g of x, where the f of x is the upper curve or line and the g of x is the bottom one. You need to know where you start and when you end. However, you should not use this point here, because if you do so, your integration is gonna come out 0. So because of that, what I'm gonna do, I'm gonna find half of this region and then multiply it by 2, which gives me the area of A. However, these points are not given to me. These two you see right here. So I have to find them. So how can I find them? Well, basically I want to know the intersection of the line y equals to 1 with this curve. So therefore you put them equal to each other. That leads to cosine x to be 0. I got the two answer I was looking for. So this is 3 pi over 2, and pi is, since it's symmetrical, pi is in the middle. Now you're gonna start with taking integration of the upper curve y equals to 1 minus 1 plus cosine x. So basically you're using this formula, and then the limits of your integration should be from pi over 2 all the way to pi, and then you double it for the reason I just mentioned. You carry on with the integration. Of course 1 minus 1 becomes 0, and you have to take integration of negative cosine x. You can take the negative outside. The integration of cosine x is sine x, and then once you apply the limits of upper and lower integration, you end up with sine pi minus sine pi over 2, and psi pi is 0, where the sine pi over 2 is 1, and the final answer is positive 2. And that's the area of the whole A. Now finding the area of B is a little bit tricky. So here what I'm gonna do, I'm gonna find this area. And now you might be wondering why I'm finding this, because again, due to the symmetrical shape of this curve, this region is the same as this region. And then once I find that, I'm gonna subtract A from it. Actually, you can double it and then subtract the whole area of A from it, and that's gonna leave you with this portion right here. So what I'm gonna do is to find this area and then double it to get this upside down bell shape, and then subtract the area of A, which is 2, and that's what I just found, and that's it. That's gonna give me the area of shaded region B. So let's go ahead and start. That's gonna be the integration of 1 plus cosine x from 0 to pi, right? Minus 1, and -1 is basically this region, and then you double it in the end, and that's going to give you the area of shaded region B. So let's continue with integration. Integration of, when you take integration of 1, you get x. The integration of cosine x is sine x, and after you apply the limits of integration from 0 to pi, you get basically pi plus sine pi minus 0 plus sine 0 minus 1, and this whole thing comes out to be pi minus 1, because sine of pi is 0, sine of 0 is also 0 as well. So I have pi minus 1. You need to double that, you get 2 pi minus 2. However, I'm not done yet, because I'm told the area of A with the ratio of the area of A to area B is 1 to k. So this is the area of A, which is 2. This is the area of B, which I just found, and that's supposed to be 1 over k. With simple cross multiplication, k is found to be 2 pi minus 2 over 2, which 2 is cancelled out from top and bottom, and I'm going to be left with pi minus 1, and that's the final answer. Question number 12. I'm given a second derivative of a curve which looks like this. Also, I'm told that the gradient of the curve is 4 over 3 at this point. So I'm supposed to find the original equation of the curve. So obviously you have to take integration twice in order to get back to the original equation of the curve. However, before I do that, because this is not in a friendly format that I'd like to work with, so I'm just gonna get rid of this power 2. Therefore, the fourth root of x in the denominator becomes just a square root of x. And also in the numerator, I expand this bracket, I get x plus 2 square root of x plus 1. And also I don't want to have any fraction at all. And since this is a common denominator, I split it into 3 terms. The first term is basically x to the power of 1 minus x to the power of half. That leads to x to the power of half. Same thing here, square root of x and the square root of x is gone. I'm left with 2. And lastly, I get x to the power of negative half. Now, if I take integration of this guy, I get the first derivative. So you basically add 1 to the existing power and divide by the new power. So you get x to the power of 3 over 2. When you divide it by 3 over 2, it's the same as multiplying by 2 over 3. Over here, you get 2x. Here, same thing. When you add 1, you get half. And when you divide a number by half, it's the same as multiplying by 2. However, don't forget there is a constant. And before you carry on with your second integration, you need to figure out the value of this constant. And that's where this piece of information comes handy, because I'm given the x coordinate of this point, and gradient is nothing but the first derivative. Therefore, I'm going to replace the dy by dx by 4 over 3, while all the x's are replaced with 1. If you do that, you get the value of c, which is negative 10 over 3. And then you carry on with the second derivative. Now, this is the expression that I have to take integration, except now c is found, and that is negative 10 over 3. Same thing, when you want to take integration, you just have to add 1 to the existing power and divide by the new power. And I have shown that in green color for you to understand that easily. In the end, again, this integration, it has its own constant. So you can use C2 to just distinguish from the previous letter, or you can just use a new letter like D, which I did here. But again, D has to be found. Now, in order to find D, we do not need to know the gradient like the previous constant. Over here, we have y, not dy by dx. This is the original equation. And the original equation of the curve, I have a point, I'm given a point up here. That's a point which lies on the curve with x and y coordinate 1 and negative 1 respectively. all you have to do is just to plug in these two numbers. So instead of y, I have -1, and instead of all the x's, I just replace it with 1, as you can see here. Therefore, that helps me to find d. Of course, I get these fractions here. I'm just gonna multiply everything by 15 on both sides. Obviously, you get all these fractions here, which you have to get rid of. I'm gonna find a common denominator for all of them, which is 15. Therefore, in the numerator, I get 4 plus 15 plus 20, right? And then also minus 50. And the summation of all these turns out to be -11/15, which when you bring it to the other side become +11/15. With this -1, that adds up to -4/15, and that is the constant, and this is the equation of the curve. That was the last question for this paper. I hope you enjoyed the video. Thank you for watching, and I see you in the future videos.